Hi, everyone, and thank you for having me here. Thank you for joining. So my name is Dimitrios. I'm from Greece, and here are a few things about me. So I'm engaged in computer security since 2002. I was a member of one of the first reverse engineering groups back in Greece, and I started my career as a network security engineer for about 10 years. Then I moved into developing for almost 5 years. And the last 5 years, I focused mainly on Android security, while before I joined Microsoft's threat intelligence team as a senior security researcher, I was leading another team which was conducting malware reviews for the Google Play Store. Besides that, I'm a father of two, a boy and a girl, and in my free time, I mostly write and play music. So before we start, I would like to address a question which I get quite often during my talks, and this is how come a Microsoft security researcher talks about Android security and all this kind of stuff. So as I said before, I have been following up with developments in cybersecurity for quite a long time. And I can assure you, although I think that you also agree with me on the fact that today's threats need a more, let's say, holistic approach. A breach in your mobile device might have much more security impact than before and can even touch your corporate's network. So I strongly believe that companies must evolve their security solutions to protect and support their clients across all platforms. So I'm very proud of being a part of such an initiative from my company, from Microsoft. And with that being said, and since we have a lot of things to go through, let's jump right into the outline of this briefing, which consists of the following topics. So first of all, we're going to talk about data and file sharing in the Android operating system using content providers. And then we're going to see what is a shared target, how it is used, and how we can identify that an Android app is actually a shared target. Then we're going to move into the main topic of this briefing, which is the dirty stream attack. We're going to explore the root cause of this vulnerability pattern and see how a third-party app can actually exploit it. What is the actual impact, which may start from information disclosure, and in many cases can reach up to code execution. And at this point, we're going to see an actual case of a code execution, how we can protect Android apps from this or similar type of attacks. And we're going to end this briefing with some takeaways. So, as you probably know, Android apps are sandboxed, each one trapped in its own data memory space, which makes data and file sharing quite hard between them. So in order to facilitate this process, the Android operating system provides a construction which is called content provider. Simply said, an app which wants to share some data can create a content provider in order to do that, while another app which wants to access some data can create a content resolver, which acts as a proxy object that communicates with the remote content provider. For this process to take place in the background and not to block the main thread, we can use a cursor loader, while the result can be obtained by accessing an object, a cursor object, which is returned by the remote content provider. So what I just described can be better visualized in the slide which I have here. So on one side, we have the server, an Android app, which wants to share some data that can be structured data or a file. So it creates a content provider and implements methods that can be used to query, insert, update, or delete data. While on the other side, we have the consumer, which creates a cursor loader that communicates with a local content resolver. And since the resolver, as well as the provider, implement the same interface, the content resolver has also methods that can be used to query, insert, update, or delete data to the remote now content provider. So after this point, these two ends are ready to communicate and exchange data. So at the application's code level, a content provider is one of the earliest created components. Indeed, if we check the activity thread class, the main method, when activity thread object gets created, the first step is to attach a looper and a handler, and next is to bind the newly created process with the Android app. For this, the bind application method will send this message to the main message queue, which is going to be picked up by the handled message. And next, the handled bind application will call the installed content providers, given a list of the content providers that this app wants to implement. For each one of them, the installed provider will create a content provider object, attaching info about the package name, the class name, the implementation class name, the process name, and most importantly, the authority, which is something like an identity that can be used to identify this content provider system-wise. At the consumer side, things are pretty much straightforward. Acquire an instance of the application content resolver class, and use it in order to perform the query. Now, regarding the query method, one of the most, let's say, important arguments is the first one, which is the content URI. So it's a URI which has a scheme, which is the content scheme, the authority part, for which I talked to you about before. We have a table name, which is something like which we can use in order to narrow down our query to a specific subset of data, and a file name in case we are dealing with a file provider. I'm going to explain what is a file provider in a few slides. The next argument is the projection, which is an array of strings with column names of the table that we want to query. So as you understand, we have a similarity with an SQL database here. And finally, as I said before, we can obtain the result using one of the get methods of the cursor class and, of course, process it. So despite the fact that file sharing can be achieved using a simple content provider, the Android operating system dedicates a specific class for this reason, which is the file provider class. And it is a subclass of the content provider. And by using it, Android apps can share files using the more manageable, let's say, and more controllable content URIs instead of the file URIs that we know so far. Besides extending the specific class, another step that an app has to take in order to share files is to declare the directory that these files reside to. In order to do that, a special file is used in XML format, which can also be used to map content to file URIs. Finally, a couple of interesting methods when it comes to the file provider class is the open file, which among others gets as an argument the content URI, and returns a file descriptor to the file that this content URI, let's say, points to. And we have also the open asset file, which, similar to the open file, returns a file descriptor, but it is used in case we want to return a subsection of a file. Right. Regarding the file path file that I said before, I want to elaborate a little bit more due to the fact that I'm going to use it while I'm describing the dirt stream attack. So it is an XML file which, with a root element, which is called paths, and some child elements, which correspond to commonly used directories by Android apps. For example, we have the root path directory, the root path child element, which points to the root directory of the device. We have the files path for the internal files directory of an Android app, the cache path for the internal cache directory of an Android app, and so on. We have also a couple of attributes like the name, which we use in order to, let's say, represent the specific child element within a content URI. And we have the path, which we can use in order to define subdirectories within the directory that this child element points to. And if this sounds a little bit confusing, I have a couple of examples. For example, we have this one, the external path, which points to the external directory. And a more complete example, I'm using content URI, the scheme, the content example as an authority, and I'm using the test root name in order to index files anywhere within the root directory of the device, including, of course, the home directory of the app, the internal directory. At the consumer side of a file provider, things are a little bit different than before. So a file provider consumer can call the open input stream or the open asset file descriptor, providing as an argument a content URI, which points to the file that wants to access. These methods are going to trigger the open file and the open asset file that we showed before. And as we saw so far, they're going to return a file descriptor, which the file provider can use in order to create a copy of the specific file to the internal or external directory and finally use it. So I said a couple of slides before that content providers are the suggested, let's say, more controllable way of sharing files and data between Android apps. And this is where also the permissions come into place. So when it comes to system content providers, like the ones which share private user info, like SMSs, call logs, calendar entries, and so on, an app must have specific permissions in order to access them. For example, to access the user contacts, you need read contacts permission, or read calendar entries, you need read calendar permission, and so on. So when it comes to third-party apps, a very important, let's say, attribute when it comes to the content providers is if the specific provider is exported or no. In case it is, any app which is installed in the device can access the data that this provider, let's say, shares. Otherwise, only apps with the same user ID can access it. Now, if you ask me, can this behavior be more manageable? Yes. You can use the grant URI permission, but if it is set to true, then an app can create an intent, attach the file that it wants to share as a stream, and use this flag in order to define a mode of operation, and send this intent to another app in order to provide temporary access to a specific file. Finally, another way to provide access to a content provider is using this method here, the grant URI permission, which gets as an argument the package name to which we want to provide access, the URI for which we want to provide access, and the mode of operation. Although I wouldn't suggest of using this method, and anyone can think of why, I'll give you 10 seconds. Yes? Yeah, I guess you need some context here. Anyway, yeah, it provides access based on the package name, okay, and it doesn't check the signature of the APK, which when it comes to App Store, right, when it comes to the Play Store apps, each one has a unique package name, which that's fine. But when it comes to off-market apps, you can, let's say, create any package name that you want, and you can get access to a file provider, which is, let's say, configured in this way. All right, so now that we have a good understanding of what is a file provider, a content provider, how we can share data between them by using them, let's see what is a shared target. So a shared target is an Android app which defines itself to handle data or files which are sent by other apps. So it's a file provider consumer, right? And we have a lot of categories of Android apps which can be shared targets. We have editors, image editors, mail clients, messenger, social network apps, a lot of categories. So to create a shared target, we have three main ways. And this is either by using an activity which matches a specific intent filter, or using the Choose Your Target service, or using the Sharing Shortcuts API. In this briefing, we're going to focus on the first one, as it is the most, let's say, popular. So to create a shared target, you must have an activity which will handle the incoming stream, the incoming file, and declare this activity in the Android manifest. The next step is to define a filter, specific filter, which filters for intents of action sent or sent multiple in case we want to handle more than one files with a single intent. Finally, we have the data type, which defines the type of the file that we want to process. In this case, for example, an image file. To send a file to this shared target, create an intent of action sent or send multiple, attach the file as a stream, define its data type, then create another intent using the createUser method, providing the first one as an argument, and finally, call the start activity, providing the second intent as an argument. So if we put these steps down, we're going to have code similar to the one that you see here. And if we execute the specific code, we're going to trigger what we call the share sheet dialog. Why is that? This intent is implicit. It doesn't define categorematically the component that this file should be sent to, so the user has to take the call and choose to which app this file should be sent to. And this is actually a practical way for you also to identify which share targets you have installed in your device. A long press on a file, choose share, and the share sheet dialog will show you which apps are shared targets for the specific file type. Right, so when it comes to handling a stream, the majority of the apps that we have reviewed so far seem to follow a very specific pattern, let's say. So this pattern consists of the following steps. The first step is to get the actual name of the incoming stream, of the incoming file. And they do that by performing a query to the remote content provider, using the URI as the first argument, and as a second argument, as a projection, using the display name, the column display name. Why this one? Because it is the one which is used by the default file provider. So developers assume that they are dealing with a file provider, and it makes a lot of sense to do that. This is going to give you back the file name. And this file name then is used in order to create another file, which is used to initialize a file output stream, and then create an input stream using the incoming URI, and finally copy the input stream to the output stream. This is a common process, let's say. Now, please notice in this case that the file name the URI, and of course the content of the file are controlled by the sender. And if you ask me how come and all these apps, let's say, follow about the same code pattern, so there is a very interesting paper by Verdi et al., which talks about vulnerabilities that were found in crowdsourced code examples, and it mentions that 69 vulnerable code snippets, which were found in Stack Overflow, were used in almost 3,000 GitHub projects. Now, I'm not saying that the code that we have here on the left, on the right, for me and left for you, is vulnerable by itself. But if you get the specific code, right, and you combine it with the copy file that we showed before, without performing some extra steps in the middle, then 100% you are going to have a problem, as we're going to see. Right, so regarding the adversary model, we're talking about an Android app that the user has to have installed on the device, and we don't need any, let's say, permission, besides internet, only in case we want to download some kind of payload or something. So we're going to use this rogue APK in order to interact with the share target. And the first step is to request from the share target to process a specific file. So as we saw before, the majority of the share targets will ask about the actual file name. What is the actual file name? Since we control this file name, we can give something like that and request, let's say, to overwrite some kind of critical file, like a library or DEX file or JavaScript file that might be loaded in some kind of web view or a settings file, and so on. So next, the share target asks about the input stream, which, as I said before, requests actually a file descriptor to it. And since we control also that, we can send a file descriptor to our payload. So this attack reminds a lot of the file upload when it comes to web servers, where we craft the file name, we craft the content of the file, we send it, and we see how the web server will handle the specific request. Here things are a little bit easier due to the fact that we have the APK, we have the share target, we have the code, we can decompile it, and we can see how it will handle the specific file. And I guess it's easier in this case. So we're going to construct this rogue APK. And in order to do that, first of all, we want to share a file. So we're going to customize our own file provider. And we're going to modify the query method in order to return our crafted name. We're going to modify the open file in order to return a file descriptor to our payload. And we will try to minimize any kind of user interaction. This is how our content provider looks like, which extends the content provider and implements the query as well as the open file methods. So starting with the query method, the first step is to try to imitate an actual file provider. And in order to do that, we add columns like the ones that the file provider has, which is the display name, the size, data, title that we saw before. And the next step is to add rows dynamically based on the incoming URI and a specific query parameter. Now remember that we control this URI, we send this URI to the share target sends this back to us. So we isolate a specific query parameter and we add rows based on it. And we do that in order to make our exploit, let's say, more general, to be able to handle more shared targets. Then we can use some kind of encoding, because in some cases, let's say an app might filter for some characters or something. So we can do also that. We attach this info to the cursor object and send it back to the requester. Now, when it comes to the open file, again, we get the incoming URI. This time we isolate the path query parameter, and we send the file descriptor to the specific, to the file that this path query parameter points to. When it comes to the payload, as I said before, we can download it from a web server or something, although the Android APK packaging provides a very convenient way of, let's say, packaging payloads, and this is the assets folder, so we can add it there and pick it up from there. All right, so we did all that in order to create a method like the one that I have here, which gets the package name of the shared target, the component that we are targeting, a URI, and creates an explicit intent this time. So this way we are avoiding the share dialog. Because we have an explicit intent, we define where this file should be sent to. So this won't bring up the share dialog. And what I didn't cover so far is the URI, how it would look like. So we have the content scheme. We have our authority, which is the com.exploit. We have a path, which we don't use, but in some cases it is used by the shared target, so we can add any value that we want here. We have the path, which points to the payload that we want to send to the shared target. We have a name for the file that we want to overwrite. We have a size. I didn't mention that it's not that important, but in some cases, the shared target might ask for the size of a file, so we can, again, control this value. We can send anything that we want back. And finally, if we are going to encode or know the specific name, the name. So if we get this query to our content provider, we're going to add a row like the one that I have here. And we're going to send this value back to the shared target. All right, so it should be understood by now that by successfully exploiting this type of vulnerability, a rogue APK can get write access to the home directory of Android app by passing this way the write restrictions of the Android operating system. And when it comes to the impact, our best chance is, of course, when the app loads, let's say, a native library from the data directory, or uses on-demand delivery modules, or loads in more general some code dynamically, or reads some critical settings from the shared preferences folder. And while there's not much to say about the first three cases, I guess the idea is to overwrite such a file that the app will load somehow and execute, so we get our code execution. When it comes to the last one, there's a very interesting behavior that I would like to talk about in regards to the shared preference implementation class. So what happened was, while we were trying to exploit the specific vulnerability type, in many cases we encountered the following issue. The app was checking if a file exists, and in that case it would abort the operation, wouldn't override the file. So there is a very interesting fallback mechanism when it comes to the shared preferences class, which can be used in order to bypass this type of check. So what happens is, when an app creates a shared preferences class instance providing the name of the file that wants to access, the constructor of the shared preference implementation class will get this file and will call the make backup file. So the make backup file will get this file and will add the .back extension to it, creating a new file this way. It will return it back, and then the start load from disk will call the load from disk. The load from disk will check if the backup file exists, and in that case it will delete it, and it will replace it with a back file. So you understand, if we have such a check, if the file exists and so on, we can simply, instead of trying to override the original file, we can create a back file and let this behavior to replace the original one with our own. All right, so when it comes to reading files, reading files is also possible, and the idea here is to try to trick the shared target to process one of its own files, and by preference one file which has some kind of sensitive info. And in order to do that, we try to exploit some kind of misconfigured content provider or loose file provider paths. But most importantly, in this case, is where the shared target will cache the specific file. All right, so what I mean by misconfigured content provider is that the application implements its own file provider without extending the default one. And since in most of the cases they don't, let's say, filter or sanitize the content URI, we can create something like the one that I have here and index some kind of a critical file. This would fail when it comes to the file provider due to the fact that the file provider will throw an error saying that you jumped out of the pre-configured shared directory, so this will fail. All right, so when it comes to the loose file provider paths, what I mean is we are looking for entries like the one that I have highlighted here, which points, let's say, to the root directory of the device. So this way, we can create a content URI like the one that I'm showing to you here. And we can, again, index some kind of, let's say, sensitive file and send it to the shared target. Now, what is important in this case is where the app will cache the incoming file. So if it caches the file, to the external directory, we can simply pick it up from there. Or there's another trick. It's called display name. It's a query parameter of the file provider class. And if they trust the specific query parameter, we can, again, use, let's say, some kind of a path traversal payload in order to force the shared target to cache the file to a directory that we control, and we can pick it up from there again. All right. Some statistics regarding the impact. Despite the fact that, let's say, this vulnerability type seems a little bit seems a bit simple. In a sample of 20 apps that we have reviewed with a common characteristic, more than 100 million installs, according to the Google Play Store, more than half of them were found to be vulnerable to this type of attack. And in 28% of them, we managed to get code execution, 18% of them, some kind of critical information disclosure, and 27% of them low to no security impact. And at this point, we're going to go through an actual code execution showcase, as I promised. And the app that we're going to review is a browser with more than 500 million installs, according to the Google Play Store. It is a shared target. It uses the doc reader activity, which is an alias for the main activity. So it has this distinctive send filter. And when this app gets an intent of action send and stream, it will finally call the method that you see here, the method I. This will try to get the actual file name by calling the method H. And the next step is to create a URI out of the incoming intents data part. Use this URI in order to create an MD5 hash, make it a string, concatenate it to the file provider string. And they do all that in order to create a temporary cache directory. Last step is to save the file under this specific directory, like you see here. Now, what stands out of this process is the fact that they don't sanitize, of course, the file name. And the result of this, let's say, mistake, this miss, can be better demonstrated here. So this app will get an intent like the one that I have here, which we suggest the name, as you see, with path traversal characters, and we'll actually cache it outside of the pre-configured cache directory. So this way, we're getting write access to the home directory of this app. We actually got. All right. So, OK, we got our write access. Now the question was what we can override, what we can do with that. So it was found that the app is using the Google Play Core library in order to deliver dynamically a plugin which uses to unzip the user files. In a nutshell, the Google Play Core library uses app bundles in order to deliver optimized APKs depending on the device's configuration. So in contrast with the legacy APKs, which might carry some extra modules that the installation device might not need, for example, libraries, stuff like that. When it comes to the bundles, they come with some basic modules, and extra modules can be installed on demand, depending, of course, on the device's configuration. That's cool because, I mean, the size is much smaller, you have better performance. But this library has a very bad habit of saving native libraries to the home directory of another app, of the app that uses it, actually. So the first idea was why we don't override such a file. Let's say, as I said before, it uses a plugin to unzip files. Why we don't override this library? They think that didn't work. The app was checking if the file exists, as I showed you before, and didn't override it. So the next was the following. The Google Play Core library uses some specific directories in order to save the APKs that download. So it has a directory which is called unverified splits, and there, when it downloads an APK, it saves it there. It verifies the signature and then saves it to the verified splits directory. So the idea was, what will happen if we save the file, if we save this plugin to the verified splits directory? To our surprise, our plugin, which had a malicious library, was unzipped, and it was used by the app. So when the user tried to, let's say, open a file, unzip a file, then we got our code execution in this case back. All right, so, and this is how our exploit looked like. So we have our APK, which, as I said before, contained this malicious library of us. And then this is actually the file that we, how we saved it, not override. All right, so when it comes to securing shared targets, how we can protect Android apps from this, even similar type of attacks. So the first thing that I suggest in that case is to ignore the display name. You don't need the display name. You don't need what is written by the, I mean, you don't need to get the actual file name in order to cache it or create some kind of a temporary file. So that's the first thing. But if for some reason you must use it, then you have to take extra steps in order to sanitize it. And of course, the first step is to filter out special characters, isolate the file name, canonicalize the cache path, and most importantly, make sure that the file which you are caching is under the directory that it should be. Right? Make sure that the actual result, the path, should be under the directory that the preconfigured, let's say, directory which you use in order to create temporary files. All right, some takeaways. Not much of rocket science here, but consider all data which originates outside of your app as untrusted. And I would like to add in this point the following, that even if you think that you are, let's say, interacting with some kind of default browser of the device or a camera app or something like that, make sure that you sanitize the data, especially when it comes to the file providers, content providers, and stuff like that. And for God's sakes, don't lock the executable files from the data directory. Avoid loading libraries, DEX files. Even if you load some kind of a JavaScript file, anything, make sure to replace them every time, for example, that you are restarting your app or something. To the users, never install apps outside of the Google Play Store. And this is due to the fact that Google Play Store ensures that apps follow some specific criteria, right? So when you install an app outside of Google Play Store, you never know what this app might carry with. And with that, that was the last one. Thank you very much. And we have a couple of minutes if you want to ask some questions. I will be happy to reply, to answer.